type 2 malware. The DeepDAR, which I mentioned, which was stealth by design, has also been implemented as a type 2 malware. So it didn't hook any code, it just modified some pointers inside NDIS data structures. NDIS is a network subsystem of Windows. So there are some data structures which have some function pointers, which points to some functions which handles, I don't know, incoming packet or something like that. And only those function pointers were modified. Actually, DeepDAR modified only four function pointers somewhere inside data section of NDIS. And fighting type 2 malware is a very challenging task. Today we cannot solve it. We have three issues here. One issue is to know where to look, because if we have this like 5 megabytes of data, there are some data which are pretty constant, and there are some data which are changing all the time. Maybe the change of some of those data means system compromise, and the change of others does not. So we need some way to know at which data we need to look at. In case of DeepDAR, there's a data structure called NDIS open block, which is a binding between NDIS miniport, which describes network card, and NDIS protocol, which describes protocol. So it's a structure which does the binding. So we need to know that such data structure and this open block could be subverted, that there are some important function pointers inside, which could be subverted to create a network backdoor. We need to know where those data, where the instances of those structures are at the moment. So we need to find some dynamic lists of those in this open blocks. And finally, we need, and then we need to look at those pointers. So at specific offsets in this data structure. So this is to know where to look. Because not surprisingly, I chose to hook like some 4 pointers inside NDIS open block, but there are like a few dozens of other places, as you might imagine, inside Windows kernel, which could be hooked to achieve exactly the same, to create a network backdoor. So we would have to have a list of all those sensitive data structures which we need to look at, which is unfeasible today. Okay, the second issue is to understand what we see. So we read those function pointers, and let's say this function pointer says OX804518E7. So does it mean a system compromise or not? Well, it depends. We need to know what is the semantic of this piece of data, and the semantic is a function pointer which should point to some valid function which does something. So we know in this case that we should look at this address and find out whether this address is contained inside a trusted module and belongs to a code section, a trusted code section of this module. Finally, we need to be able to read memory. This might be surprising because we all know how to read memory, don't we? Because computers are just Turing machines, right? This is what I actually just said, and this is also what I just said, and this is about reading memory. So as we know, computers are just Turing machines, so what's the problem in reading the memory? But actually there are some complications. Because if you think about a software-based detector or a verificator, we usually think about kernel driver or a loadable kernel module, which does this job. Well, alternatively, it might be implemented as a hypervisor to make sure it can be subverted, but it doesn't matter. What matters is that to read the memory, which is occupied by the operating system, and we are just something other. We are a third-party program which tries to access the memory which is occupied by a system. We need to properly synchronize with memory manager. You might think, okay, but we cannot break anything by just reading memory. But actually we can. And like 1 year ago when I was working on SVV, I saw several crashes, system blue screens, just because SVV was trying to read memory without properly synchronizing with memory manager, and that created some very weird race conditions. Also, the other problem is that if we are a program, even assembler, even looking from the assembler point of view, we can only access virtual memory. We don't have access to physical memory. And there was a nice example of Shadow Walker rootkit, written by Jamie Butler and Sherry Sparks, which implemented virtual memory cheating. So even if another program running as root, using machine instructions like move to read the memory, this program was getting a fake contents of memory. So to overcome this, we need to have a way to access page directories, so PD, and some others on 64-bit processors in a reliable way. But to do that, we need to follow CR3 register, and CR3 register contains physical address. And actually, there is no easy way to convert physical address to virtual address without relying on default OS mapping. So we can, some people can say, okay, there's no problem because CR3 points to some address, physical address, and usually on Linux that would be CO something something for page directory. But assuming that the operating system is intact, but attacker could have modified it, operating system virtual memory manager, so the page address to virtual address mapping could be different. So we have also, if not software-based detector, we could consider hardware-based detector. Just recently, it has become very popular to use FireWire to access memory. So FireWire or PCI card, they all use DMA, direct memory access, to get access to the actual physical memory without the CPU. So CPU is here is the device, like PCI card, here is memory, and device just directly talks to the memory and gets the contents of memory. This is very good because it's very reliable and it doesn't require any additional software on the target system. However, we cannot read paged out memory this way. And also, I wouldn't be so sure that it's actually that reliable, but this is something I'm gonna talk about later next year. Because of those three things I said, know what to look at, understand what to look at, and be able to reliably read memory, today we cannot systematically, correctly detect type 2 malware. Or in the other words, we cannot verify system against type 2 malware. And that's actually the proper topic of this lecture, towards systematic verification of the operating system. So our goal is to change the design of the operating system a little bit so that it will be possible for us to create a detector, software-based or hardware-based or hypervisor-based, doesn't matter. Actually, hypervisor-based is almost like software-based. The only difference is that it's not prone to implementation-specific attacks. So we want a recipe to create a detector, let's say software-based. Detector which when we run against a particular system on this very laptop, then at this very moment it would return a verdict, 0 or 1. System is clean, or system is compromised, and by compromise we mean type 1, type 2, or type 3 malware. Oh, I didn't say anything about type 3 malware. I'm just leaving it for the end of the presentation. So this is what we want. Of course, still, even if we had such an ideal detector, of course, still we could have type 0 malware, which could be botnet or something like that installed on the system, or something which deletes our files in home directory every other week. But again, as I said, type 0 malware, for me, this is just an application having some weird features, right? But this is not something which compromises the other operating system components. I want to verify that the other operating system components are not compromised. So the biggest problem with creating such a detector, or such a verificator actually, is type 2 malware. And this is a problem because operating systems are too complex. So we don't know what to check, and we cannot reliably read memory. So maybe we could change the rules a little bit. How about if we introduced the following requirement? The following requirement which always should be satisfied in a healthy operating system. That would be, the requirement would be, the only executable pages in the system, let's say kernel for now, are those which contain trusted code. All other pages should be marked as non-executable. I want to focus on kernel for now because this is not that easy in case of some user mode applications like JIT compilers, binary translators like VMware, and etc. So let's leave them for a moment. So for now, I want this requirement to be introduced into operating system. Why this is so useful? It is so useful because if you think about type 2 malware, you should think about type 2 malware as a malware which hooks some function pointers in data sections, right? So no matter, of course, we agree all that we cannot verify all those function pointers. We cannot find all those function pointers and verify where they point. So instead, we want to make sure that all the code in the kernel, we want to make it possible to verify all the code in the kernel. So if somebody modified some function pointer and points to some other things, some code which does some malicious things, make sure that we could find out that this is code which is not signed with our trusted certificate. So the complete requirements for the operating system would be, there would be 4 requirements actually. The first would be that the underlying processor must support non-executable attribute on a per page level. For example, AMD 64. Operating system must maintain strong data code separation on page level. So in a clean operating system, there should not be any page containing, well, let's say it differently. In a clean operating system, there shouldn't be any kind of data which is kept on a page with executable attribute set. There must exist some way to verify code on a per page level, and in practice that means digital signatures implemented. How this is actually implemented, I mean how this PKI is implemented, which CAs do we need to trust, this is beyond the scope of this research. This could be like, we could set up in our own detector which certificate authorities we trust and how much we trust, etc. But basically we need some way to verify that on this page, and we need to do this on page level, on this code contained in this page passed or not passed the digital verification. And finally, operating system must allow to safely read raw memory by a third-party program.